yet draw ever near. Air of earth, mark of fear, felt to be.
Hey, Kaposi Gloves here, and today we're going to be doing some physics problems. Let me go to my iPad here. Okay, here we are. These are our problems. We've been given the general cases of flat surface force. So I'm in a physics class right now, and I'm going to solve these three problems. This is the first set of problems of the general cases. What does this general thing mean? Well, it means there's no numbers. They're all symbols. And so if I'm given numbers, I'm going to be like extra good because I could do it all symbolically. And at the end, I just have to plug the numbers in. So very, very good way of understanding things is if you can understand the general case, you can go at the specific cases a lot easier because general cases focus on understanding of principles. So we're going to solve these three problems, and we're going to start with the first one. Now, these are easy problems. I'm also going to do them the way I need to do them on the test. So you might not have to show as much work as I do, but in a way, it's a good thing because now you'll see more. So let's go ahead. Let's read our problem. An object of mass m, so we're given the mass m, is acted upon by a force F sub a. So we have some force here along a horizontal, so we're going horizontally, and we're on a smooth surface. So smooth surface, just as a side note here, right? That means our friction of coefficient, our coefficient of friction, what the heck was that, is 0, right? We're not accelerating horizontally. And then we say, okay, given this, calculate the object's acceleration. So we want to know the acceleration. And so the way I have to do it is I have to make these columns. I need a column for my given variables for what I want, a diagram, and then I need some equations. So let's go ahead and let's first tackle our given information. Now, when you're solving a general case, there is a rule. The rule is whatever your answer is, it's got to be given using only given information. Meaning if we're going to accumulate more variables over here in the diagram portion, and I cannot have any of the variables we get over here. They must all be variables from the given portion. So we're given a couple basic things. We're given the mass. So we're given mass. We are also given the force F sub a. We know our friction of coefficient is 0 because we're on a smooth surface. So since it's smooth, we don't need to worry about this. It goes away. And also we know that we're in a gravitational field. This is just, we're on Earth, so we're in a gravitational field. Our next column is to be determined. So to be determined, we put an A in there because we want to know the acceleration. What's the acceleration? What is A? And now we are going to jump into the problem. So the first thing, so we're going to do right now a free body diagram, meaning that we're going to have an object with a center of gravity, and all the forces are going to come from this center of gravity. And that's a free body diagram. So we're generalizing whatever object it is to just sort of this box with a dot. So first, let's go ahead and draw our surface. So to do that, I'm just going to put a surface down. And then I'm also going to put these lines to indicate that it is a surface. Okay, now we need the next step you should do. If you have a surface, you should always draw your surface first. And then we're going to draw our object with a gigantic dot. And this dot is the source of all our forces because we're concerned about what's happening to this object. So we know amongst the first of our forces, we have a force of gravity, and gravity always goes vertically down, and we show it at our box because that's obviously the gravity we're concerned with affecting our force, our object. So our object, we have gravity, so we need to label this. Now this gravity is actually this green vector I just drew here is actually the weight. And so weight is the mass times the acceleration due to gravity. So we're going down, but our object says, it's being accelerated along a horizontal smooth surface. It is not going up or down vertically. And we have this force and another force called the normal force. So we know that these forces must be balanced. So they must be the same size. And my instructor literally takes out a ruler and measures this. So we're going to kind of eyeball it, but she will mark you down if you're like a centimeter off. It's like kind of crazy. So I guess a centimeter is kind of a noticeably big difference, but yeah, you want to make sure they're the same, right? Because we're not moving horizontally. Our object stays, we're not moving vertically. Our object stays horizontal. It's going to be going that direction, right? And then we're told one more thing. We are told that our force is acted upon, and we are going this way with our force, right? So this is our force. We label it. We should label everything. And there's no friction. There's no resistance to our force. So our object's going to go in the direction our force is applied. So we have our gravity and our... By the way, I keep these colors consistent. It's a good habit to get into. I try to keep red for the forces acting upon objects, gray for my normal force, and green for whatever gravity is. Okay, so this is what we have here. Pretty simple. There's a couple other things I have to show. Otherwise, I'm going to get big points marked off. And you will probably for this one too. But that's which direction is positive, right? We don't know. So I'm going to declare up as positive and to the... What is this? This is my right. I'm not sure how this comes across on YouTube with the whole screen being reflected thing, if it's the same or not. And then, okay, I should show, she calls them helper axes. My y, these become much more important in other problems. But here they're just sort of, we just need to have them. So we have y and x, right? This is our axes. So when we say horizontal, we're actually referring to the x axis. So this tells us where the f sub a is. All right, so that's our diagram. We're all done with our diagram. There's nothing else we need to worry about here. But now we have a pretty clear picture of what's happening. And we also should do a magnitude check. And so we just need to check that our gravity, our mg, is the same as our normal force. And we're just going to go with it's good for us. It looks pretty okay. So now we're going to go over to our last column. And I'm going to label it. This is our equations. So we have equations. And we only have one object. So fortunately, we only have to worry about one. And we know that we have two axes, right? So this is an important step. I have to show this as well. We have x and y. And what we're going to do is we're going to go f net x. So what is this? Well, we know that from the second law of motion that we're going to have the net forces against the up and down, which is the y-axis. So we have up and down forces. We have left and right forces. And we can tell if an object is going to move if the forces are balanced or not. So vertically on the y-axis, they are balanced. And so that means our object doesn't move. It's zero. It's at rest. So later on in other problems, we will use this to get additional information. But for now, we are fine. And now we need fx. Well, fx is f net x is unbalanced, right? So it's not balanced. So that means that mass times acceleration, ma. And so now our a is showing up. And so this is what we're trying to get. Now we look at our thing here, our free body diagram, and we say, well, F net x. What is that? F net x is all the forces on the x-axis. We only have one. That's F sub a. And that's equal to ma. And there's no other forces here. So our answer actually just ends up being F sub a, and we divide by our mass. And that is our acceleration. That's it. So there we have it. Very, very simple. And now we need to check, though, is our mass given and is our F of A given? And we look back at our given column here, which is right here. And we say, yes, they are all in that column. So we are good to go. This is an answer. We can put that on our test and we will get our points. So there we go. There's our first case, right? Easy peasy, a lemon a squeezy. We ended up not needing our y-axis. Now we're going to build on this case a little bit. So on to case 2. Okay, an object of mass m. So again, we're given m is acted upon by a force F sub a. We'll highlight that. That's important. Along a horizontal rough surface. So that means that we're going to have some mu sub k. We're going to have some coefficient of friction, right? Determine the object's acceleration. Okay, so we want acceleration. If the coefficient of friction mu sub k, so there it is, between the object and the surface. Oh, if the coefficient of friction is mu sub k. So, okay, we say, all right, let's do our columns here. So we say, okay, here's a column, diagram, and then equations on the other side. So we have given, and so we need, well, not need, we are given, we have our mass, we have a force F sub a, and it's along a horizontal surface. We don't really write that over here. I mean, we could, I guess, in theta if we wanted to, but it's given by a horizontal surface. And then we say, all right, the object's acceleration is what we want. So that goes in our to be determined column. We want our acceleration. We're also given that we now have a friction of coefficient. And then finally, we also know we have a gravitational field. Now, you might be going like, wait, that's not in the problem, but you know, you're on Earth. It's a given thing. Now we're going to do our free body diagram. Step 1, we are going to, whoops, move my screen around. We are going to draw our surface. It's just what you do at the beginning. We have a surface, so you draw it. Later on, I'll probably do all these slanted cases as well. And then we'll get into pulleys and a bunch of nifty stuff. I'm not sure how far I'll go. But anyways, you draw your surface first. That's all I'm saying. If you have a surface, you should draw it. Okay, so there's our surface. Now we need our object. So we draw a big box or a box, just a box. It doesn't have to be a rectangle, just a box. And we have a big dot. The dot's the important thing. They want to see this dot. So this is where all our forces originate. By the way, yeah. Just checking to make sure I put the helper axes up there. I forgot if I did or didn't. Okay, so we have our box. And we could put our axes on now. So, right, we have an x-axis going through the box. And a y-axis going vertically up. And down. So there's our helper axes. We think, okay, so here's our box. The first force I like to put down generally is gravity. So I'm going to put down some gravity force. Make it not too crazy big. And there's gravity. Da-da-da. And we know that gravity is, this is the force due to gravity, really. So it's the mass times the acceleration due to gravity downward. We also know that any problem with this is going to have a normal force perpendicular to the surface. In this case, it's going to go up, and it's going to be at the same, it's going to be the same size as our mass, as our gravity vector here. And you might be going, well, why? Or I guess I should be calling it the weight vector or something. But you might be going, why? Well, that's because we're not accelerating vertically. So it's got to be the same. So we'll just try and make it the same here. Sometimes you have to adjust it. We do a magnitude check at the end. And then, of course, we need our force. So we know our force, right? We're accelerating. I'm going to accelerate this way. And there we go. So there's our force F sub A. I also did not label our normal force. That's a bad habit. Or not a habit. That's just bad. Don't do that. So, okay. And then we also have a new force. We have the force, the coefficient of friction, mu sub k. It's sub k, not sub s, because our object is moving. So we say, all right. Now we know that our coefficient of friction, our friction force, has to be smaller than our F sub A force. And the reason is we're moving in that direction. So the coefficient of friction's force is always opposite the direction of motion. So we are going this way, and I drew it quite small. And its symbol is F sub K, and it's the lowercase f. It has to be a lowercase f. If it's like some other f, you're going to lose points. So don't do that. Okay. It's just a standard symbol that people know what that means. If you use uppercase f, then, you know, it's like, what the heck? We have a special symbol for this. All right. So there we have it. We have our vectors. We need to declare now, you know, what's our positive and negative direction. So we say, okay, positive will go up, and positive we'll go, what is this? To the right. So, all right, up and to the right. And I believe we have everything we need on here. So we'll go over here to our equations. So now we've got our equations. And we have X and Y because it's a X and Y coordinate system. So we have X and Y equations, naturally. And so we could split up. We know that. And so we're basically treating each one as a separate dimension. We know we're going to have F net X for the X dimension. And so that's going to be, now this is an unbalanced system, right? We're accelerating this way. That's the direction we're going. So this is going to be unbalanced. And an unbalanced system, by the second law of motion, states that we're going to have ma, mass times acceleration. And then we say, okay, well, on the Y, we're going to have F net Y. And we're not accelerating or moving in the Y direction. So that's at 0. So we say, okay, cool beans. We got these things. Now let's go ahead. We want the acceleration, which is over here. So we're going to work with that equation. So F net X. Well, our force F sub A. Okay, so that's really quick. Let's explain. How do we replace this? Well, we look at the vectors on the x-axis. So we notice we've got the friction over here and the force over here. the force is moving in the positive direction. The friction is moving in the negative direction. And when you sum them together, you're going to get this. That's what the second law of motion is saying. So we say, okay, here's the force F sub A. We're going to take away the friction F sub K. That's going to give us the mass times mass acceleration, whatever. So there you have it. There's our formula now. And you might think, oh, we could solve for A now, but we can't. We can't because this is not in our given column, F sub K. Mu sub K is given in our given column, not F sub K. So we can't say this. It's not given. So we come back over here and we say, all right, cool beans, dude, man, bro. All we got to do is figure out what F sub K is. And we know that F sub K is mu sub K by the normal force. So this is, I mean, we could get into what this means, but when you're solving the problem, generally you just think, okay, friction coefficient against our normal force, that's going to give us our force of friction. I mean, if you think about it, because the normal force is going to be some force going up against the object. Well, not against the object, but off the surface from the object. And the friction coefficient is going to be the rubbing that takes place as the object, resists. And so we've figured out that this describes that relationship. And so we say, all right, friction F sub K. Well, we don't know. We don't know this. So we made this into that. But now we don't know the normal force. So now we've got mu sub K, but N, we do know, you might be going, well, we do know the normal force, it's over here, but it's not in our given column. So to find the normal force, we go to where the normal force is involved, and that's on the y-axis. So it's on the y-axis. So we're going to go F. Okay, so we look on the y, and we're going to sum them together just the way we did the F net x. So we say, well, N, the normal force, and that's positive because it's going up, according to what we said in our diagram, minus the mg, which is the weight of our object, right, going down. That's got to be negative because it's going in the negative direction. So it must be negative in your equation. So n minus mg, that's equal to 0. And so we solve for n and we get mg. So now we say, aha, this is actually, the normal force is actually just mg. So now we can substitute in. We can say, well, let's do this in steps. So we say the force of friction is mu sub K times mg, because that's what n is. So we say, okay, that means that let's go ahead, let's substitute F sub K back into our equation. We have F sub A, our force, minus mu sub K mg, because that is what F sub K is. It's this. And that equals ma. And then we can go ahead and do our last step here. I'm just copying it over and dividing by the mass. That equals our acceleration. I need to sneeze. All right, I'm all done sneezing. So we look over here and we say, are all these variables in our given column? And we say they are. They are. So we have found the answer. This is what the acceleration is. Now, these answers can seem kind of crazy, but it makes sense. If you're given, if you're given these things, maybe they're, you're given numbers, you could figure it out. And if you know this, they could ask for a number of other things. They could ask for the force. Maybe they don't give you the force, but they give you all this other stuff or whatever, You could figure it out just by doing some algebra. So really, really helpful to know the general cases. And now we have one more. This one is the hardest of the three. It's still not that hard when you get into later problems. It gets much worse. But these are the ones you start with. So we say, all right, let's dive into our last one. We have an object of mass m. So we say there's that m is acted upon by a force F sub A. That makes, here we go, an angle theta with the horizontal. So we say, oh my gosh, we've got angles now. Great. If the object accelerates along a rough, so we have a friction coefficient, horizontal surface, and there it is, with a friction coefficient mu sub K, calculate the object's acceleration. So that's what we're looking for. So we're going to do it like we did the others. We have our 3 columns, 1, 2, 3, and then equations on the other side. And so we say, all right, well, what are we given? Well, we're given that we have mass, right? And we're given a force F sub A, and a force is a vector, and vectors have direction, and we're told this time the direction's theta. And since it's not what a typical force, it's not along an axis, we actually make a note of that. We put it as, because this is how you would notate it, right? So we have our our vector with its direction next to each other. We are also given that it accelerates along a rough horizontal surface, and we remember that was mu sub k. And we want to know, to be determined, TBD, the acceleration. We also have one other thing we know. We know that we're in a gravitational field. So there we go. There's our given variables to be determined. Now we move on to our free body diagram. Step 1, make a surface, right? Always do that. If you have a surface, make it. So there's our surface. La-di-da-di-da. We put our lines here to indicate it's a surface. And then we make the step 2. You always make your box with a dot. Box with the dot goes next. So we have our box with a big freaking dot right there. Look at that. It's like a giant zit of physics. And then we say, all right, now I'm going to do the helper axes next. And the reason is I want to get theta in this business, right? We're going to do gravity first, but let's put down our helper axes, get those out of the way. So here's X, here's Y. Now these, sometimes also you'll put these in at like the very end. They're sort of like, oh, gotta have those. Well, not true. When you do slants, you put these on like right immediately because your x-axis is no longer a horizontal axis. It's like slanted. So they're more important. Okay, so let's go ahead and put down gravity. So gravity's green. And so we put that down. Boom, gravity. And we label it mg. And now we need the normal force, right? Because we have a force perpendicular to the surface. So we say, here's our normal force. Woo! And we're going to make it the same as gravity. But it might not be the same as gravity when we're done here. You know, we're going to have to check some stuff. So we say, okay, there's our normal force and there's our gravity. Now we need to make well, let's do our friction coefficient first. So we know we're going to be accelerating, and we know we're going to be accelerating this direction. So with that in mind, let's go ahead and put our friction coefficient in there. I'm going to make it small. Generally, you want them small. So there's my small friction coefficient. I am doing this because if you do not make it this small, you may regret it later because you'll have to readjust a bunch of vectors. Your life can get hard if you make this too big. Sometimes you want it big. It just depends on the problem. In this case, making it small probably save us some aches and pains. Another thing I noticed here is my gravity vector is slightly smaller than my normal vector. I'm going to make that a little bit longer. You might be going, wow, that seems like a really small thing. But in my class, like, man, I don't even know, man. You just got to be careful. She really knows exactly what she wants. And I guess that's a good thing, I guess. Okay, so here we go. We're going to now make our force F sub A. It's going to be at some angle, right? Whoa. Here's our force F sub A. Actually, you know what? This force is enormous. Let's make it smaller. But make it, you know, pretty big for reasons, the same reasons we made F sub K so small. It's our force F sub A. And it makes an angle F sub A. It makes an angle theta with the horizontal. So we say, oh, look, there's the angle theta. Now, we cannot have vectors just going off into weird directions like this. Like we don't know what to do with this. Like how do we determine what f net x and f net y are? Like we don't know. So what we do is we resolve the vector into its component vectors. And so what that just means is we take it and we split it up so that we split the vector up using our vector addition. Well, a vector addition would give us this vector. We're going to make it into two vectors such that when we put them together, they will give us back this vector, right? And that allows us to know how much force is going along the x and the y axes. Now, the way we do this visually is I'm going to move my theta like in here more. Okay, so the way we do this visually is you draw. This is a, what do you call this thing? An altitude. So you draw an altitude and it makes a right angle with your axis. And then we draw another altitude, right? This time it's going to go this way. This is for the y component. It's going there, right? And then we always draw our forces originating at the center of mass, so at our big dot. So that means that we have a force originating here that goes up. And this is our force F sub A y. So this is F sub A y. Sub A y. This is the y component of our vector. And then we have another force going this way, and this is our force F sub A x. And we're going to use some trig to get these exactly later. But remember vector addition, if I were to slide this vector over here to fill in the triangle like this, our vector addition would result in our original vector, the f sub a. So we know we drew our vectors correctly. But now we have a couple problems here. So we've got all our forces on this diagram, but we have some problems, right? So we know our object is moving in this direction. And so we check our x-axis and we say, well, this friction of coefficient is quite small, and our x component of our force is much larger than the friction of coefficient. So our object will, given these forces, move this direction. However, if we look at our y-axis, we have our normal force going up, and we also have our y component of our original force, F sub a, also going up. So it's n plus F sub a y are both going up. This is visually bigger. If we were to take F sub a and tack it onto the end here, right, we'd have like some vector like that long. That is much bigger than our gravity is. Our gravity can't hold this down. So in order to not lose points, we need to make our gravity vector larger. So we need to make this, it's kind of sad when you say sentences like that, but it also makes sense visually, right? It's also correct. So I'm just going to say, sure, why not? This looks about the same. If it like really mattered, we're saying that this distance of green line is the same distance of this gray line plus this red line. It's good enough for government work. On a test, I'd be like freaking out, sort of making measurements and making sure. But this is good enough for like just the purposes of an example. Whoops. And then, okay, so now let's go over here and declare our directions. We're going to declare up as positive and to the right as positive as well. And then another big thing, you need points. You'll lose points if you don't do this. So we have everything. Finally, we've got it all. Let's go ahead over here and make our equations. So we say, okay, equations. On our equations, we have our x and our y, x, y. You notice I made these a bit bigger. We're going to have trig functions. That's why. So we know with these of our two pieces, we're going to have a f net x. Hopefully you see the pattern here, f net y. We are not accelerating on our y-axis. That was why we moved the gravity vector around like that, is we're not accelerating. So that's going to be 0. But our f net x we are, and whenever a system's unbalanced by this second law of motion, we put an m sub a, or not m sub a, m times a, mass times acceleration. Okay, so now we're going to replace f net x with all the forces, because this is the sum of forces. That's what net means. So we're going to say, okay, well on the x-axis, our f sub a, our f a of x is positive. So we say, okay, well that's going to be f a of x. That's our positive force. And friction is resisting it, right? So that's going to be minus our friction, which has to be a lowercase f. Again, just giving you a warning. That equals ma. All right? Well, now you might be going, why are we ignoring y? Well, because y doesn't have anything we want. We want the acceleration. So we're going to work with this one. So we say f sub k. Well, we've been through this before. This is the same thing as mu sub k times the normal force. And we say, holy crap, we don't have the normal force. So we're going to come over to our f net y to do this. Before we do, actually, let's go ahead, let's do that. So we have f net y. So now we need to replace this. So we know that in the positive direction of our forces on the y-axis, we have the normal force, and we have the vector component f sub a y, right? The force, the vector component of the y. So we know that we have the normal force plus the vector component on the y-axis. And if we subtract from that our balanced force, I made this an A down here. This should be a G. I don't know if I've been saying G or A. I can't remember, but it should be G because that's gravity, right? So if we take those two forces sum together, because they're moving in the positive direction, so they have to be positive, and this one has to be negative, so it's moving in the negative direction, we'll get 0. That's the point. Now here we have this AY thing. This isn't going to fly, right? How are we going to get our force back from some mysterious Y over here? So what we're going to do is we're going to use trig to eliminate this Y. I keep drawing arrows to the Y, but that's what we're going to get rid of. So we come over here and we look and we say, I'm going to outline theta. Here's theta. And so I think what trig function will give me y? And so I'm not going to go into great depth here on what this means. I guess you can drop it in the comments, a question, if you really want to know. But we can replace y. So we have fay. Well, y is the sign opposite. If I were to take this vector and move it over, it would form the opposite side of a right triangle, which means we can use trigonometry. So we could say fay is the same thing as fa sine of theta, because it's opposite. And then our hypotenuse is our vector. So we can use sine theta to do this. So fa sine theta is the same thing as fay. So we're going to go ahead and put that in there. These subvariables can be somewhat confusing. Trust, I lost some points on the first exam just because I didn't get them. But I have resolved those conflicts in my head. So we have n plus fa sine theta. We know this is actually sine theta for all the trig I just explained over here. So minus mg equals 0. All right. Now we just got to solve for the normal force, right? So that's normal force is going to equal positive mg minus fa sine theta. So we say, great, we know what the normal force is now. We can come over here and plug that in. So we say, okay, here's our friction coefficient anew. It's mu sub k times mg minus fa sine of theta. All right, cool. So there we have our friction coefficient. We could take this and we could plug it back in up there. So now we have this, let me do this in red. We have this here x axis. We can get rid of it the same way. So if we look at this, this is this, I'm going to outline it in black on our diagram. This part of our vector component, fax, well, this is the adjacent side, right? And we know that cosine will relate our adjacent side to the hypotenuse, which is our original vector. And we know our original vector. So we can figure out this fa sub x is the same thing as fa cosine of theta. So this will give us this will be the vector component on the side. So we're able to break it down to an actual number instead of this mysterious x thing. So it's for the same trigonometric reasons as the other one. We're just using the cosine value to figure it out. So hopefully you're comfortable with trig. So we say, okay, here's fa, and I'm copying it from up here, right? Fa, except for now, this is cosine of theta, because we've figured this out. So cosine of theta, and then minus and f sub k, which is our friction. So we say, okay, well, that's parentheses mu sub k. I guess parentheses aren't totally necessary here, but hey. That's mg, our weight, minus the vector component on the y-axis, which is sine theta. And then I'm going to erase part of this just so, we're not crossing this bar here. Okay. That's going to be equal to our mass times our acceleration. So I say, oh my gosh, we're almost there. So I'm going to rewrite this one more time. F sub a cosine of theta minus mu sub k times mg minus fa sine of theta all over, we divide by m because m was over here, but we've divided by it, so now it's over here, and that's it. Woo, buddy, we are there. It sounds a lot worse when you explain it out loud, but hey, that's how it is sometimes. I didn't like the fact that it turned out to be a circle thing. Whatever. So there you have it. That is the answer. That is how you do these problems. So just a quick recap. You draw a surface. You draw your diagram. Don't forget your helper axes. Don't forget to define the direction. Resolve any weird component vectors. Draw your forces. I generally start with gravity. Don't forget the normal force. Make sure your final answer. So here, all this stuff. Now you might be going, what about, this is not in our given column, but f sub a is in our given column. And this is a form of f sub a, so we're fine. What's not fine is f sub a x. We can't put that in our answer. And you might be going, why can't we put that? Well, we can't get a number from this. So we can't put that. But we could put this because this will resolve to a number. And since we know f sub a, this is enough information for us. So that's why that's that way. So as long as your answer is in terms of everything in our given column, which it is, you're good to go. So now if you're ever given any numbers and it follows one of these general cases, you literally can just figure out what the formula is and just plug in the numbers at the end. So that's sort of the idea behind general cases. They're a great advantage to a huge number of problems. The general problems just in general. Hashtag YOLO, subscribe, and have a blessed day.